In one of the most remarkable discoveries of the 20th century, we learned that the universe is not a static, unchanging framework but instead dynamic, with space itself expanding as time progresses. This means that distant objects are moving farther apart, and this phenomenon is observed uniformly in every direction. Nearly a century after this revelation was fully understood, it remains a perplexing and fascinating enigma, even for astronomers and astrophysicists. The expansion of the universe raises profound questions. What happens to space itself as it expands? Does it stretch thinner and looser? Or is new space being created to fill the gaps left by expansion? If the universe has been expanding for billions of years, what is it expanding into? Are we, as observers, expanding alongside the universe? These questions are some of the most challenging to visualize in modern astrophysics. Fortunately, recent data from the James Webb Space Telescope offers insights that may help unravel these mysteries. The foundation, general relativity. To understand these cosmic phenomena, we start with Einstein's general theory of relativity, the modern framework for gravity. General relativity connects two seemingly unrelated concepts: the distribution of energy in the universe, including matter, antimatter, dark matter, radiation, and neutrinos, and the geometry of spacetime itself, whether and how it is curved and how it evolves over time. In a universe devoid of any matter, energy, or radiation, spacetime would be flat and unchanging, resembling a simple Newtonian-like space. However, introducing even a single mass distorts spacetime, creating curvature. For example, placing a point mass in the universe would warp space in a predictable way, as described by the Schwarzschild metric. Similarly, if the mass were spinning, spacetime would twist in a more complex manner, following the rules of the Kerr metric. These spacetime models, though intricate, are static. Their structure remains constant over time, meaning the distances between points within the spacetime and the size of phenomena like event horizons do not change. However, the universe we observe is far from static. A dynamic universe. Homogeneity and isotropy. Our universe, on large cosmic scales, exhibits two critical properties: isotropy and homogeneity. Isotropy means the universe looks the same in all directions, with no preferred orientation. Homogeneity means the universe has a uniform distribution of matter and energy, with nearly identical density, temperature, and expansion rate across vast scales. Given these properties, general relativity dictates that the universe must either expand or contract, as shown by Alexander Friedmann in 1922. This expansion or contraction depends on the distribution and types of energy in the universe. Observations confirm that our universe is indeed expanding. What does expansion mean? The expansion of the universe doesn't mean galaxies are moving through space like objects in a wind tunnel. Instead, it means the very fabric of spacetime is stretching. This stretching increases the distances between galaxies without them traveling through space. However, space itself is not something we can measure directly. Instead, we observe how it affects matter, light, and other measurable phenomena. For example, light traveling through the expanding universe experiences a redshift, where its wavelength stretches, making it appear redder. This effect has been confirmed through observations of distant galaxies, the cosmic microwave background radiation, and even light from stars orbiting black holes. These measurements align precisely with the predictions of general relativity. The role of matter and energy in expansion. As the universe expands, the total amount of matter remains constant, but the volume of space increases. This causes the density of matter to decrease over time. General relativity's calculations confirm this relationship, which matches observational data. However, not all components of the universe behave like matter. For instance, radiation, quantized as photons, has its energy determined by its frequency. As space expands, the wavelengths of these photons stretch, reducing their energy. This phenomenon is also consistent with general relativity. The nature of space and the future. One of the most intriguing aspects of the expanding universe is the question of what space itself is doing. Is new space being created, or is existing space stretching? Observations suggest that space behaves like a dynamic, flexible fabric, influenced by the energy and matter within it. This understanding raises profound philosophical and scientific questions. What is the universe expanding into, if anything? What will the ultimate fate of the universe be? Continuous expansion, a slowing down, or even a reversal into contraction? Recent findings from the James Webb Space Telescope provide new data to explore these mysteries. The telescope's ability to observe the universe's earliest light and distant galaxies offers insights into the mechanics of cosmic expansion and the distribution of matter and energy across space and time. Conclusion: the expansion of the universe is one of the most extraordinary phenomena in modern science. Challenges our understanding of space, time, and reality itself. While general relativity provides a robust framework for understanding this cosmic evolution, many questions remain unanswered. With cutting-edge tools like the James Webb Space Telescope, we are steadily uncovering the secrets of the universe, bringing us closer to comprehending the profound nature of existence. As the universe evolves and light travels through its ever-expanding fabric, several fascinating phenomena occur. The universe's volume increases, while the total number of particles remains constant. However, each quantum of radiation undergoes a shift in its frequency toward the redder, longer wavelengths of the spectrum, an effect known as redshift. This redshift, a key indicator of the expanding universe, has been observed in every quasar and galaxy measured beyond our local group. Additionally, our universe is influenced by dark energy, a form of energy not associated with particles but inherent to the fabric of space itself. While we cannot measure dark energy directly as we do with photons, we can infer its value and properties by observing how redshift evolves with distance. This relationship between energy types and the universe's expansion rate allows us to estimate the amount and nature of dark energy. Current findings suggest that dark energy accounts for roughly 2/3 of the universe's energy density today. Unlike other energy forms, the energy density of dark energy remains constant, even as the universe expands. Combining data from various sources paints a consistent picture. The universe is expanding at a rate of approximately 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of separation between objects, the expansion adds a redshift equivalent to a recession velocity of 70 kilometers per second. By examining objects at greater distances and measuring their redshifts, we can reconstruct how the expansion rate has evolved and determine the universe's composition throughout its history. Composition of the universe. Today, the universe consists of the following: 0.8% radiation, primarily electromagnetic radiation in the form of photons; 0.1% neutrinos, which now behave like matter but acted as radiation when their mass was negligible relative to their kinetic energy; 4.9% ordinary matter, including atoms, plasmas, black holes, and all matter formed from protons, neutrons, or electrons; 27% dark matter, whose exact nature is unknown but which appears to be massive, gravitationally bound, and behaves like matter; 68% dark energy, an intrinsic property of space itself. By extrapolating backward based on today's data, we can identify the dominant forms of energy at different stages in the universe's history. Observing how the expansion rate has changed over time also provides insights into the universe's past and future. With sufficient observations, we can better understand its ultimate fate. The cosmological crisis and dark energy. Despite significant progress, new data from telescopes like Hubble and James Webb suggests that the universe's expansion is occurring faster than our best models predict. This discrepancy, often referred to as the Hubble tension, has been building for years. Some researchers propose that resolving this tension might require adding a new component to the universe's inventory. One leading hypothesis involves early dark energy, which suggests that around 50,000 years after the Big Bang, there was a brief burst of dark energy. This temporary energy surge could have influenced the early universe's evolution enough to explain the Hubble tension without requiring major changes to the standard cosmological model. However, this adjustment would slightly revise estimates of the universe's age, reducing it from 13.8 billion years to about 13 billion years. Other researchers, such as Dr. P.K. Sesh and colleagues, argue that integrating quantum effects into our understanding of general relativity might resolve the tension. These effects, tied to random field fluctuations and particle creation in the vacuum of space, could alter predictions about the universe's early expansion. While detailed calculations remain challenging due to the elusive nature of quantum gravity, these efforts open the door to experimentally studying these effects in the future. The expanding universe. Into what? The observable universe, defined by the expansion rate, the speed of light, and the time elapsed since the Big Bang, represents only a fraction of the total cosmos. As light from distant regions continues to reach us, the observable universe's volume will more than double. However, the universe itself might be infinite, rendering questions about what it is expanding into irrelevant. The theory of inflation suggests that our universe is one region within a larger, inflationary multiverse, with each region experiencing its own Big Bang. Yet, the universe isn't expanding into this multiverse. Rather, its expansion is an intrinsic property of space itself. Locally, gravitationally bound systems like galaxies and galaxy clusters, such as those in the Virgo cluster, do not adhere to the rules of universal expansion due to their internal gravitational forces. Only unbound systems experience the full effects of cosmic expansion. On the largest scales, space expands uniformly, governed by its inherent spatial properties. Ultimately, the universe's growth reflects the dynamic nature of its own structure, with no external space required for it to expand into.